Hi, Year 11, let's look at your paper 4 now. So, in question 1, you are given a diagram showing a swimmer in a river. The river is flowing to the left on the page, so from east to west. The swimmer, originally their position is that they are swimming towards the north. Starts at point P and swims at a constant speed of 0.72 meters per second relative to the water and at right angles to the current. Determine relative to the river bank. So the river bank is where the river meets the land, so that's the horizontal. Relative to the river bank, so relative to the horizontal, both the magnitude and the direction of the swimmer's velocity. So we know that without any current flow, the swimmer would just swim up the page, north. But the river is going to also be translating over because of the current flow. And so while the swimmer forces an upward direction and the river forces a to the left direction, the swimmer is actually going to drift diagonally, and we're trying to find the resultant of that. So let's have a little look. We can see it is just a vector diagram. So the resultant velocity comes from the two individual component parts. So we've got the swimmer moving at 0.72 meters per second up this way. 0.54 meters per second is at right angles. And I could have drawn a scale diagram. That would have been absolutely fine. So I could have chosen to do maybe a 7.2 centimeters and a 5.4 centimeters diagram, measured the resultant that way, that would be fine. But to save a lot of time, because it is a right angle, I can just use Pythagoras theorem. So I know that if I have a right angle triangle, a squared plus b squared equals c squared. So I can say that 0.54 squared plus 0.72 squared must equal the swimmer's resultant direction velocity squared. And then it's a simple case of substituting in, and you get to 0.9 meters per second. So because every second the swimmer goes 0.72 meters per second north and 0.54 meters to the west, in total their displacement in 1 second is going to be this resultant. It's going to be 0.9 meters every second. So that's the velocity magnitude. Now, because it is asking relative to the river bank, so here's the resultant, and then the river bank is this dotted line, the angle that I need to find is theta 2. The easiest thing to do is to find theta 1 using trigonometry, and then knowing that there's a right angle between the 0.72 and the river bank, I can just find the difference from 90 minus that angle. So first things first, I can use tan theta 1 is equal to the opposite over the adjacent. So that gets me a value for theta 1, which works out to be 37. But because it asks relative to the river bank, the direction, I need to do 90 minus 37 to find what theta 2 is, getting me 53 degrees. Then after 1.5 minutes, the swimmer reaches point Q. Calculate the distance between P and Q. So 1.5 minutes needs to be converted into seconds for this to work. And then it's a simple case of distance travelled is speed multiplied by time. So whatever value of velocity you've got here gets substituted in, and then that gets multiplied by the 90 seconds, gets you to 81 meters. If you've got the same value as me, but you would have got carried error through here. In question 2, excuse me, a student investigates the efficiency of a filament lamp. So you've got a diagram showing the filament lamp with its glass bulb immersed in water in a beaker. The reading on the thermometer in the water is 19 degrees Celsius. Only the glass of the lamp is in contact with the water. The electrical components are completely insulated. The lamp is switched on, so we know that energy is going to dissipate into the water. At the end of the experiment, the temperature of the water is 21.5 degrees Celsius. So I can immediately see there's been a temperature change, and I can calculate that, and it's 2.5 degrees Celsius. In A, it says the mass of the water in the beaker is 600 grams, and the specific heat capacity of the water is 4,200 joules per kilogram per degree Celsius. The clue here is that you've got a kilogram value, so you need to convert your grams into kilograms. So 600 grams is 0.6 kilograms. And then to find the increase in thermal energy, you're using your specific heat capacity equation. So E is mc delta theta, or mc delta T if you want to remember it that way. So we know that the temperature change was 2.5 degrees Celsius. That gets you one of the marks. One of the marks comes from remembering which equation you're going to use, and then one for correctly plugging in. So the mass was 0.6. C, the specific heat capacity, was 4,200. Delta theta, or the change in temperature, was 2.5. Gets you to 6,300 joules. In part II, let me zoom in a little bit. In this experiment, the lamp is switched on for 500 seconds. This is a time value, label it T. The power supplied to the filament is 13 watts, that's P. The useful energy from the lamp is transferred as light. The energy that increases the temperature of the water is wasted energy. Determine the maximum possible efficiency of the filament lamp. So the first thing is to work out how much energy in total was being supplied by the lamp by looking at its power rating and multiplying by time, because energy transferred is power times time. 13 watts for 500 seconds means that the lamp was able to supply 6,500 joules. That got you 1 mark. Lots of you mistook this and assumed that this value here was your useful energy. It wasn't. It tells you that the energy used to increase the temperature is wasted. So the useful comes from the total minus the wasted, which is 200 joules. That was worth the second mark. The third mark came from listing the efficiency equation, is useful output over total input times 100. And then it's substituting the numbers in. The useful was the 200 joules transferred as light. Total input was 6,500, and that gets you to 3.1%. In B, it says the efficiency of the lamp is less than the value determined. So we need to think about this. At the moment, what we've said is that electrical power is being transferred through the light bulb being switched on in the form of light and in the form of heat energy transferred into the water. This is not the whole picture, because we know that the water itself will then be at a temperature that's higher than the surroundings, and there will actually be transfer of energy out to the surroundings. And so some of the energy is also wasted to the surroundings. This is why it's even less efficient than we've considered before. So we need to say the reason that the efficiency value is actually lower than that is that there will actually be more energy losses that we've not thought about. Thermal energy will also be lost to the surroundings. In question 3, figure 7.1 shows a circuit that contains a battery, a switch, a voltmeter, and 340 ohm resistors R1, R2, and R3. The switch is open. So at the moment when the switch is open, R3 is not part of the circuit. So R1 and R2 form a potential divider. So you can imagine, just completely ignore this section. What you have is your power supply, and you've got R1 and R2 as a loop in series with a voltmeter over R1. Part A for 2 marks asked you to describe what is meant by a potential divider. This was worth 2 marks. We wrote this down in our books literally a week or 2 before your mock. A potential divider shares the voltage or splits the voltage of a power supply. 1. The second mark is explaining that it's split between 2 resistors, and we looked at this. We looked at all the possible combinations. It could have been 2 fixed resistors, a resistor and a variable resistor, a resistor and a thermistor. Nonetheless, it's always 2 resistors in series that we split the voltage through, and that's worth your second mark there. So that was just a basic recall. So it says the reading on the voltmeter is 7.5 volts. Calculate the EMF to the voltage value supplied by the battery. Now there's no internal resistance, so we know that the resistors are all identical because they're 340 ohm resistors. So at the moment the switch is open, R3 is not in the circuit. So we have a power supply supplying voltage to R1 and R2. And we are told that this is reading 7.5 volts. If these are identical resistors, they will take an equal share of the voltage, which means that R2 must also have 7.5 volts. 7.5 plus 7.5 is 15 volts. This was done pretty badly. So make sure that that makes sense. Come and find me if it doesn't. The switch is now closed. Calculate the resistance of the complete circuit. Okay, so step one is to work out if this is closed, we now have a complete circuit. So if we look at the possible pathways, sorry, it's a very squiffy line. If we are a charge, we can come around. We have to go through R1. At this junction, we can either go through R3 and come back, or we go through R1, R2 and come back. This is a parallel section. We can find the total resistance of this parallel section by using our 1 over R total equation is equal to 1 over this resistor, which was 40, plus 1 over this resistor, which was 40. This gets me 2 out of 40. To get to R total, I have to flip this fraction. It's 40 over 2, 20 ohms. So together, this section is worth 20 ohms. R1 is 40 ohms. So the total resistance of the circuit is the 40 ohms and the 20 ohms in series. Gets me 60 ohms. So you get 1 mark for the value being correct. 1 mark for doing 40 plus whatever you said R2 and R3 were worth. So even if you got that wrong, you can have a mark there. And then 1 mark for correctly identifying that R2 and R3 together make 20 ohms. So then it says, calculate the reading on the voltmeter when the switch is closed. So we know that when the switch is closed, the voltmeter now is going to read a different number. So it's not going to read 7.5. Okay, we know that this is a 15 volt supply now because we worked it out in part B. We know that this is a 40 ohm resistor and this section is worth 20 ohms. So this is going to take a 40 out of 60 share because the total resistance was 60. R1 is only 40 out of that 60. So it takes a 40 out of 60 share of the total available, gives me 10 volts. In question 4, we are told a helicopter is stationary at a height 1,500 meters above the ground. In part I, state 2 conditions necessary for the helicopter to remain in equilibrium. This was a memory game. I told you if it ever asks you what the conditions are for an object to be in equilibrium, all you have to write is that there is no resultant force and there is no resultant moment on the helicopter. 1 for each there. The mass of the helicopter is 3,200 kilograms. Calculate the change in gravitational potential energy of the helicopter as it rises from the ground to 1,500 meters. A surprising number of people got this wrong. You just need to remember your equation. GPE is mg delta h. The mass was given, G is 10. Delta H is given in the question. Substitute in 48 million joules. In part B, this was a little bit more difficult. You have a figure showing a speed time graph for a parachutist who jumps from a stationary hot air balloon. The parachutist jumps from time t is 0 and reaches the ground at B. The point A indicates when the parachute opens. On figure 1.2, label a point on the graph where the acceleration is. Okay, so the first thing is we need to remember that if we have a speed time graph, the gradient of the graph represents the acceleration at that point in time. So we're looking for where the acceleration is 0. So we are looking for the gradient being 0. We're looking for where the graph is horizontal. So you could have had anywhere in this section where it's horizontal or this section. That's where you could have labelled a 1. Where the acceleration is negative, I need a negative gradient, so I need the slope to be negative. So anywhere in section 2. The acceleration decreasing means the gradient is decreasing, getting less steep. So you can see that the gradient is getting less steep here, and it's also getting less steep here. So anywhere you see 3 with the red line, the gradient is decreasing, therefore the acceleration is decreasing. Explain in terms of forces. I've talked to you about this. If it says in terms of forces, you better have the word force or specific forces referenced in your answer, or you won't get any marks at all. A lot of you were talking about energy, and that's not what the question is asking for. So it says, explain in terms of forces the changes in motion which occur from when the parachutist leaves the hot air balloon until point A. Okay, so we know that there can be two forces at play the whole time. The weight of the parachutist acting downwards and the air resistance as the parachutist falls through air acting upwards. Initially, there is only weight. So at the instant that they jump out of the hot air balloon, they've not hit any air yet, and so the only force is weight. Then obviously as they fall, they start to hit air particles, air molecules, and the air resistance force is increasing. But to begin with, their weight is still significantly larger than the air resistance. There is a resultant force, therefore, the weight is larger than air resistance, the resultant force is down, and therefore there is acceleration. The second mark comes from stating that we know that air resistance increases if velocity increases. If you're moving through the air faster, there are more collisions per second, the force from the air is increasing. The third mark comes from saying that when air resistance increases, this decreases the resultant force, and therefore it decreases the acceleration. And then the fourth mark is for saying that when air resistance is equal to the weight, so once that value balances out, there is no resultant force and the parachutist has a constant velocity. So in each case, I'm looking at the forces and how they change, and then what that does to the motion. So look, in each statement, I've got a reference to a force and something about the motion. Weight, acceleration, air resistance, velocity, resultant force, acceleration, air resistance and weight, constant velocity. So in each statement, I'm referring to how the forces change and then what that does to the motion. In question 5, a student catches a cricket ball. The speed of the ball immediately before it is caught is 18 meters per second. The mass of the cricket ball is 160 grams. Immediately convert that into kilograms, please. Calculate the kinetic energy stored in the cricket ball immediately before it is caught. You remember the equation. Kinetic energy is a half mv squared. A shocking number of people forgot the squared factor. 1 mark for recalling the equation, 1 mark for the mass conversion into kilograms, and 1 mark for the correct answer being 26 joules there. In part B, it takes 0.12 seconds to catch the ball and bring it to rest. The final velocity is 0 meters per second. Calculate the average force exerted on the ball. Impulse is change in momentum, which we know can also be calculated from force multiplied by time. So, mv take u, which is the change in momentum, is equal to ft. To find the force, I rearrange for f, and I get mv take u divided by t. So then it's just substitution of numbers in. V, the final velocity, was 0. U was the initial velocity, which had to have been 18 meters per second, you're told at the start of the question, and it happens in 0.12 seconds. Okay, and so the average force value was 24 newtons. So 1 for recognizing the equation, 1 for your correct final answer. In C, as the student catches the ball, she moves her hands backwards. Explain the effect of this action on the student's hands. So you actually had to refer to both the force and what that does, so the force and the time. The ball is in contact with the hand for a longer period of time, so the force is smaller on the hand. So you have to refer to the fact that moving the hand backwards means that the ball can stay in contact with the hand for longer while it's slowing down, and therefore for the same change in momentum, the force will be smaller, so it won't hurt as much. In question 6, a detector of radioactivity is placed in a lab. There are no radioactive samples. So the student notices that the detector is still showing a count rate that varies between 20 and 24 counts per minute. Suggest a source of these readings. It's background radiation. Explain why these readings are not constant remember we wrote down that radioactive decay is spontaneous and it's random. Okay, so it'll happen by itself if something is radioactive. You will get the decay, we don't have to have any input on that. The source will decay, but it's random. We can't tell when the next atom in a sample will decay. Okay, and so it's the word random that you need in your answer there. A nucleus of uranium U contains 92 protons and 146 neutrons. This was perhaps the most disappointing question on the paper while I was marking it, because it's really straightforward, but the overwhelming majority of you got this wrong. It decays by emitting an alpha particle, okay, and they even give you the symbols for the elements in the alpha particle. Complete the nuclide equation for this radioactive decay. So many of you were writing 146. The top number is the mass number. It's protons plus neutrons. You have to add these together to get 238. And then the bottom number, your atomic number, is your proton number. Okay, that was where your first mistake was. An alpha particle I've asked you to remember is 4,2. If you don't, you're going to get this wrong. You basically got 1 mark for each of these being correct. Okay, but this is just something that you need to memorize. And a lot of you hadn't done that. In question C, an isotope of radon has a half-life of 3.8 days. It decays by emitting alpha radiation. Calculate the time taken for 16 milligrams of this isotope to decay to 2 milligrams of this isotope. So step 1 is working out how many half-lives have to occur to go from 16 to 2. Well, 16 will decay to 8 after 1, that's halved once. 8 will then halve to 4 after the second half-life, and 4 will decay down to 2 milligrams in the third half-life. So we know that we need 3 half-lives. If each half-life is worth 3.8 days, we just need 3 lots of that, getting us 11.4 days. This was a tricky question, so I'm less frustrated if you get this one wrong, because it was difficult. This is really what distinguishes your A-star students. Figure 9.1 shows the current potential difference graphs for a resistor, a thermistor, and a filament lamp. So we can see we've got current and we've got voltage. And we can see we've got 3 components that we can look at. So we can see a fixed resistor has a constant gradient. So as the voltage increases, the current increases proportionally. For the thermistor, as the voltage increases, the current is increasing at an increasing rate. And then for a filament lamp, it's the other way. So at higher voltages, we're getting a bigger stretching current. Okay, don't worry too much about interpreting that at this point. We can take it step by step. The resistor, the thermistor, and the filament lamp are connected in series with a power supply. Again, this is a blessing of a question, and too many people were losing marks here. Draw a circuit diagram for this circuit. This is just a simple case of remembering the symbols and drawing it in correctly. A power supply, remember, that's DC and that's AC. If it said a battery, it would mean that you then draw a battery. I've given benefit of the doubt, but you need to really be paying attention. So we get 1 mark for having 4 components in series. So drawing a series circuit, even if your symbols are completely wrong. 1 mark comes from having correct symbols. Too many people were drawing variable resistors and not thermistors. Okay, so we've got our fixed resistor, our thermistor, our lamp. It doesn't matter what order they're in, so long as they're in series. Okay, so then it on the next page says, add a voltmeter to your circuit diagram in AI in a correct position to measure the PD, the potential difference. I told you that you need to be familiar with that. It means voltage across the resistor. And again, so many people were forgetting that voltmeters go in parallel. We know this. Okay, so you then go back and you add for your resistor, not your thermistor, not your light bulb. Just look, it's asking for it across the resistor. So you needed to add a voltmeter in parallel with your resistor here. Okay, too many people were adding this in series, which was quite shocking. So the part III, which is where the 4 marks are really challenging to get, using the graph in figure 9.1, determine the potential difference across the terminals of the power supply when the PD across the resistor is 6 volts. So what it is asking is it's telling you that the resistor value is 6 volts. And then it's saying, well, what has to be being supplied by the power supply from there? Now, the clue is, and this is why it's difficult, it's a series circuit, which means that the current is the same everywhere in series. So if the resistor has a voltage of 6 volts, I go to my graph, I look at where the resistor has 6 volts, and I track across to see that the current through it must have been 0.4 amps. But what that means is if 0.4 amps was going through the resistor, it must also have been that there was 0.4 amps flowing through the thermistor and the light bulb. And so I can go across at 0.4 for each component and mark where the line is. I can then read off the voltage value for each component. So I already knew that the resistor was 6 volts, but I can now see that the filament lamp was 3 and the thermistor was 9. Okay, so let's add that onto my diagram. I've got 9 volts for this one and I've got 3 volts for this one. I know from Kirchhoff's law that whatever voltage is picked up across the supply is transferred across the circuit. And so I'm going to add these 3 together, 6, 9 and 3. And when I add those together, I get my 18 volts. So to be clear for where the 4 marks came from, it was 1 for recognising that the current would be 0.4 amps from the graph, 1 for recognising the voltage values for the lamp and the thermistor. You actually got a bonus mark if you even got one of those right, and then the final mark came from adding them all together. In B, it asked you to describe a practical use for a thermistor. Lots of you were just describing how a thermistor works. A use is what do we use it for in real life. So any of these are good options, and descriptions of how it works not really relevant. You could have said use it as an electronic thermometer, use it for temperature control. It operates a fan in a computer that switches on when the temperature gets too hot. A fire alarm or a thermostat, all options. I suggest you just memorise those if you didn't get those right. Okay, question 8. Figure 7.1 shows a ray of light approaching face AB of a glass prism of refractive index 1.5. So we know that the light has started in air, where n is 1. When you see the ray of light reaching the face AB at this point, step 1 is to always draw a normal line at that point. So you get your protractor, you measure 90 degrees and you draw your normal line. You need to do that to be able to find the angle of incidence for the ray of light. You can see then that refraction has occurred, and it says on figure 7.1, accurately draw the path of the ray within the prism from face AB to face AC. So you are being asked to draw this line. You will need to make a measurement, so that was where you measured your angle of incidence, and carry out a calculation. That is a clue that before you do anything, you need to have done both of those. Too many people were just drawing random diagrams and not really thinking this through. So 1 mark came from recalling Snell's law. n1 sine theta 1 is n2 sine theta 2. Before the light enters the prism, n1 is air, is 1. The angle of incidence is sine 60. We are told that the prism n2 refractive index is 1.5, which means that we can work out the angle of refraction. I can rearrange the equation and I can get a value for theta 2. So you got 1 mark for carrying out this calculation, okay, and working out 35. You got 1 mark for correctly identifying your angle of incidence was 60. You then literally needed to measure your angle of refraction, so I'm drawing that in purple now, between the normal and the refracted ray needed to be 35. 1 mark for that correct value there. Okay, and then it was 1 mark, which was very kind of them, that even if you did all of that wrong, if you knew that it bent towards the normal, you got 1 mark. And then it just says, in part II, determine the angle of incidence of this ray when it strikes face AC. So, again, at AC, it strikes where I've just put my cross. I draw my normal line at this interface. The angle of incidence, the incoming ray, is now this angle that I'm gesturing at. You measure it with a protractor. It's 10 degrees. In question 9, Let me see if I can get everything on the page. Hopefully it's not too far away. 3 identical dishes, A, B, and C, contain an equal volume of water. Dish A is outside in sunlight and experiences no wind during the day. Dish B is outside in sunlight and experiences a strong wind during the day. Dish C is in a dark room. Water evaporates from each dish. After 12 hours, the student measures the volume of water in each dish. Dish C contains the largest volume of water and dish B contains the smallest volume of water. Explain, and again, look, they've given you a clue, in terms of particles, why the 3 dishes have different volumes of water. So you need to refer to particles in your statements. You can see I've underlined that, so you can see that it's included in each mark point. So step 1 is for actually explaining what's happening to particles if they are exposed to sunlight. So particles exposed to sunlight have got thermal energy being transferred to their kinetic energy. Okay, so particles' kinetic energy is increasing because sunlight transfers thermal energy to their kinetic energy. 1 mark. Mark 2. It is the particles with enough kinetic energy that are able to escape from the surface during evaporation. Part 3 is explaining that the wind will remove particles from the air above the liquid, making it less likely for them to lose energy and be able to return to the dish and re-enter the liquid. And then the last mark was, you could have had any of these points for the mark. Let me zoom in so that actually you can see all of it. You could have said wind increases the rate of evaporation, sunlight increases the rate of evaporation. You could have said that dish C has the lowest rate of evaporation or dish B has the highest rate. If you say all of these, you don't get 4 marks. They're all worth the same mark point there. Okay, but it's really about explaining the physics behind the evaporation and then finally explaining the difference between them, which I do understand is tricky in this question because the question is really asking, well, why do the dishes have different volumes? But you've always got to go back to basics and explain the fundamentals first, which is why people were losing marks there. Okay, in question 10, figure 6.1 shows a converging lens and an object, OX, so that's given here. The focuses of the lenses are labelled F. On figure 6.1, carefully draw 2 rays in bold. If you draw more than that, you're not following the rules, you will not get the marks, from X, which locate the image of the object. Draw the image and label it Y. Measure the distance from IY along the principal axis to the centre line of the lens. Okay, so we firstly need to remember that we've got our rules for ray diagrams. If the ray comes in parallel to the principal axis, it comes out through the focal point. If the ray goes through the centre of the lens, it carries on without any change in direction. And so we need to draw these 2 rays first. We then need to backtrack because our eye is silly. If we're looking from over here, this light appears to have come from up here. Where our dotted lines cross is where our image is formed. Our object is in front of our focal point. We get a virtual image. It's like a magnifying glass. Okay, so then we draw our image. Okay, measure the distance IY along the principal axis to the center line of the lens. You are going to measure from here to here, and you're going to measure that distance. It's 3.4 centimeters if you've done it correctly. I should also have been more careful. Here is I, here is Y. Okay, the marks came from 1 for each ray being correctly, that's not a sentence, sorry, grammatically. 1 for each of these rays being drawn correctly, 1 for extending back, and then 1 for your correct measurement along the axis. Okay, in question 11, in A, tidal power gets most of its energy from the moon and part of its energy from the sun. State one other source of power which derives its energy from the sun. Don't list all of them, I'm just showing you what your options were. Fossil fuels derive their energy from the sun because fossil fuels are literally, we're burning fossils, so plant matter and animal matter that has been fossilized. We know that living things get their energy from the sun because we eat meat, which has at some point eaten a plant. Plants get their energy from photosynthesis, which is the sun. Biofuel, again, it's burning matter that we grow in the ground, which gets its energy from photosynthesis. Hydroelectric power requires the water cycle. We need evaporation of water so that we get rain, so that we have water flow down through rivers and on mountains in our hydroelectric dams. Wave power, again, we have tides and tides flowing because of gravitational attraction to the sun and the moon. It's just like tidal. Solar, again, is pretty obvious. It is the sun transferring its energy straight away. State one source of power which does not derive its energy from the sun. You could either have had geothermal, which is energy stored within the earth, or nuclear power, because we're releasing the energy from uranium or plutonium. So in B, figure 3.1 shows a small water turbine driven by a tidal flow of water to generate electrical power. Explain whether this method of generation of electrical power is renewable. Loads of you lost a mark because you didn't say yes or no. You went straight to the explanation. So whether or not it is, you have to say yes or no. So 1 mark for yes, and then saying that, well, tides will always occur. The sun is always going to exist, so this is an unlimited resource for your 2nd mark there. In 12, which is our last question, explain in terms of the momentum of the particles. Again, we need to be really reading the command terms in the question. If you don't refer to momentum and particles, you're not going to get the marks. So check your wording. Do you have those words in there? How does a gas exert a pressure? So you needed 3 out of 4 of these points. Start with the fact that moving particles, I've referred to the word particles, must have momentum by virtue of the fact that they are moving. I've now referred to both things in my answer. Great. Momentum of the particles will change when the particles collide with the walls that the gas are contained within. 3rd mark point, force is rate of change of momentum. This is an equation that we wrote down. So we wrote it on your equations keyring like this. Okay, that's just one to remember. And that also pressure is force per unit area. In B, we've got the temperature of a sample of gas is increased at constant volume. State and explain any change in the pressure of the gas. Well, firstly, we've got a fixed volume, but we're increasing the temperature, which we know means that the kinetic energy average of the particles has increased. They're moving with more velocity on average, so there are going to be more frequent collisions. The pressure increases 1. That's the statement. The explanation is what I've just said. Particles at higher temperature have higher kinetic energy and velocity during collisions. Therefore, they have a bigger momentum change. In C, another sample of gas is in a sealed container of volume 170 centimetres cubed and exerts a pressure of 9 times 10 to the 4 pascals. The volume of the container decreases by 70 centimetres cubed. Too many of you didn't read this carefully and read this as the new volume is 70. It's not. The volume decreased by 70. So if we started at 170 and we lose 70, we must now be at 100 centimetres cubed. That was worth 1 mark for recognising. The 2nd mark comes from remembering that if we have constant temperature, then PV is constant. P1V1 equals P2V2. Then it's substituting in. We have our original pressure and volume. We don't know our new pressure, but we do know our new volume. Rearrange, and you end up with 153,000 pascals for the final mark.